So we resume from the initial data problem, and what we have found is that in the CTT approach, the Hamiltonian and the momentum constraint are equation 3a and 4a, which is that we interpret as an equation for this x vector and an equation for the conformal factor psi. So what I want to do now is to show you that we can obtain known black hole solution using this formalism. And some of these solutions are actually then useful to discuss other things. So in particular, I'll focus on equations that have no matter content, and I said this E and P in this equation equals 0. And then we said that we have free data. The free data are written there. And here we make a choice. And we choose, in some sense, the simplest choice that we can do. So the conformal metric, we take it as the flat metric, the 3 flat metric. The TT, the transverse traceless A tilde ij, we just take it 0. And the trace of the extrinsic curvature, we take it 0 as well. So what happens when you make this choice to the equation? So first of all, if this conformal metric is flat, everywhere you see around a covariant derivative of the conformal metric, this is simply the covariant derivative of the flat metric. So if you use, say, Cartesian coordinate, this is simply partial I. This enormously simplifies things. For example, also L tilde, the operator there, it's the operator with the flat, with respect to the flat metric. And if ATT is equal to 0, you have, for example, that, where is it? Okay, no, this later. If k is equal to 0, that's what I wanted to say. What you see here from the 4a equation is that the equation for A and for 3 are coupled. But if k is a constant, they decouple, in the sense that you don't have this psi to the 6. So you may, if you pick this constant, you may solve first for x and then calculate from xa and plug it in there, so it's partial decoupling, but you can solve them in a decoupled way by doing first this and then that. And of course, 0 is a particular constant. So with this, you simplify many terms. So 3a and 4a actually simplify. And what you get is something that you can solve at the blackboard. That's where you do it here. You have the flat Laplacian operator on the conformal factor plus 1/8. Here you have Lx ij, Lx ij, psi to the minus 7 equals 0. And you have xl, this is now not the conformal L, it's just L, psi I equals 0. Okay. So these are the equations that we want to solve, but to solve this equation we need conditions. And I'm going to solve this with different, I'll show you sort of hierarchy, starting from very simple data to actually different, slightly more complicated data, which of course will also give more interesting solutions. So one common assumption for all this derivation that I'm going to do is the asymptotically flat condition. So what you ask is that your sigma slices asymptotically, so for large R, are flat. So these are conditions that are completely natural if you look for a solution for isolated objects. If you have an object any object, at the center, and then you go very far away from it. These are the conditions that you want. And the natural condition is that, say, a special infinity, the conformal factor is 1, and the xi is 0. And this is at special infinity, so a very large R. So if you take only this condition, so now we go through cases. The first case is just we try to solve this equation just with this asymptotically flat condition, which means effectively we are solving on R3. Then, in this case, so a solution of for A, for x equals 0, is x equals 0. The equation is linear, so you're done with that. Then this means that the solution of the other equation is just the Laplace equations, with just on R3 with just boundary condition psi equal 1. So the regular solution is psi identical equal to 1. This is the simple case, but what this means is that in this particular case, you have just recover a slice of Minkowski. Which is perhaps not particularly exciting, but it's good that we get it. So you can do something more interesting. For example, you can try to solve the equation in R3 minus a ball. So if now this is R3 and you have a ball here, let's say a surface S with a normal SA or SI. So this you exclude from the domain, which means that you don't have only the asymptotically flat condition, you also need to say something of the field in this S. And then you can do many things, but for example, you can take one interesting condition that I already gave it to you, or that we study now, is xi on the ball 0. And if we take now the conformal factor again equal 1, of course we fall back in that case. So we have to take something else. An interesting choice is to ask that this surface is minimal, which means that the divergence of the normal vector is 0 on S, of course, and which means in practice, what if you now calculate this, and I did it for you, it gives you this type of boundary condition. Say on some radius, radius A, it gives you this type of boundary condition. So this is a mixed Dirichlet-Neumann boundary condition. So you have a derivative and the field combined in this way at R. And so what you want to do now is to try to solve, so of course if you take x equals 0 also in S, you have it at asymptotically flat R plus infinity. You have at R equal A equals 0. So a solution here is again x equals 0. So what you remain is again what you have is again the Laplace equation equals 0, but now the Laplace equation has a boundary condition here, has a different boundary condition. And so in this case, the equation of, so the solutions is again, in this case, x identically 0, but phi is the 1 over R thing in this case. And A is a constant, and you want to try to interpret this constant. One way to interpret this constant is to calculate ADM integral. So this ADM integral is an integral defined in a way that I'm writing on a very large sphere that you send to infinity. So let's call it, let's just indicate it in this way. It's not the same as, but okay. To infinity in conformal, so typically here you have an expression which is involves derivative of the metric, but in conformal variable, in case of conformally flat, in case of conformally flat metric, the expression is actually this. And you have to send r plus infinity. What you find is that this thing actually is a alpha. So you interpret this constant as the mass. So you cannot call it m. And you interpret this constant as the mass of Schwarzschild isotropic coordinate, because this is what you have found.
This is A over 2 or 2A?
Sorry?
A is m over 2, no?
A is m over 2, yes. And what you have found is actually...
So this is m, so it's 2A.
2A, yes. So A is m over 2, yes. So the integral, it's 2A, correct? Yes. Yes. You interpret it like this because effectively you have x equals 0, which means A equals 0, which means k equals 0. So extrinsic curvature is actually 0. And gamma is psi to the 4. So it is this quantity times the flat metric in spherical coordinate, and this is a slice at, say, a time equals 0 of Schwarzschild in isotropic coordinate. Okay? Where your r goes from m alpha to plus infinity. So how to proceed from here? What you can do, there are different, so if you do for example, the Kruskal diagram, now this is Schwarzschild r to m, here you have r equals 0. What you have found, or what we have found, is this piece here. And a nice way to represent it and it's starting to get messy. So a nice way to represent it is through embedding diagram. So what this means is that you fix theta, or you eliminate theta, and then you have a two surface which you embed in R3, where in the vertical direction you have the radius, in the let's say horizontal direction you have the phi, and that the embedding diagram of that slice is something like that. So this goes r plus infinity, and this is r equal to m alpha, which is the minimal surface that here we have assumed, but in fact, gives that surface at that point. So one thing that you can do with this, since we are exploring solution, since this is a minimal surface, you can think about taking a copy of this and glue it below. First, I'll draw it and then explain like this. Okay, and the way you can do this in practice is to consider the transformation r prime, yes, m square, the same m square divided by 4r. So now you have that r prime goes from 0 to 2m. To m alpha. And you see from this transformation that if you put m half, this thing is maintained. It's the same. So with this transformation, what you can do is to copy every point from up to down, and these points actually are gluing. They remain the same. Also, the transformation keep this minimal surface invariant, and you also discover, if you look at that, this is an isometry of the metric. So in this way, you have calculated another solution, which corresponds. Okay, it's too far. Which corresponds to region 3 of the Kruskal diagram. If this was covering region 1, the yellow one now, so the one above is the red line there, which is this. Now the yellow is, you continue by that x-axis on the left, and you enter the third region of the Kruskal diagram. So this r equals 0 is another asymptotically flat end, which is let's say brother or cousin of the r plus infinity. So this extension is yet another solution of the problem. So you can call it 3. And the funny thing, or the good thing of 3 is that Gesundheit. The funny thing of 3 is that the equations are linear. You just have this, right? So you can consider this a black hole solution in some sense, but you can superpose them. So linear equation. Yeah. So you can superpose solution. You can say that the conformal factor is 1 plus the sum of as many holes you want, n, each with its own mass and center on a certain xp. With the factor 1/2. I definitely don't have in the notes, but it's here. And this factor here, it's indicated as psi bl, and this is the Brill-Lindquist type of solution. So what you have these things. You start from 1, but then you can attach as many as you want, but each has its own asymptotically flat end. So this is an interesting solution. This is actually used. It was used in the past for numerical evolutions. So if you want to do a black hole collision from rest, for example, you can take these two, superpose them in this way, and then evolve it.
The isometry, is there an isometry here or not anymore?
In this one, I don't know this. This I don't know. I would have to look at it on top of my head.
But what is the condition that they should be far away?
No, there's no condition here. This is a perfectly valid solution of the constraint under this hypothesis. I'll tell you what is the difficulty with this data now. So the difficulty. So first of all, these are called Brill-Lindquist data. Okay, and they are also are data of type that they are called time symmetric. Or also data with a moment of time symmetry. These are same type of words, same meaning, different words for same meaning. And the reason for this is that k is equal to 0, which implies that the derivative of the, this is equation 1, imply the derivative of the metric is 0 at t equals 0. So it's time symmetric for this reason. There's a symmetry t minus t. If you want this happens every time you have shift equals 0, because the difficulty, and these are perfectly valid and can be used for non-collision at rest, for example, but the difficulty is that you cannot have momentum here, for example. So you cannot, these two things are not, they evolve. By the way, it doesn't mean static. The data is time symmetric, but can evolve. So if you, if you put these guys, for example, if you set them like this, they do evolve. They will go against each other.
Is it what Han and Lindquist
Yes.
use?
Yes, this is what they use. There's another, actually, I'm not sure, but there's the Misner data.
Yes.
Okay, so there's Misner data, which is a similar construction, but much more involved, in which the asymptotic end is common. So it's more complicated to do. And now I don't remember which one of the two, but I think they use this. So the problem is this, that when you have these data can have a non-trivial evolution, so they are not trivial data, or they are not static, in any case they are not static solution. But with this, because k is equal to 0, you cannot have movements. You cannot boost them, for example. They don't have spin. So what we learn from this is that if you want to do more general collisions, whatever this means, you need k ij different from 0. So we can now consider another type of solutions. It's a type 4. Okay, and this is a solution due to Bowen-York. 80. What they did, they considered the same problem, but they took R3 minus, let's say, 1 or more point. So it's not the ball anymore, but also that is not the ball. So it's something that is similar to that, where you have just points removed. And what they propose is say, okay, here, in this particular case, we can find a solution of how's it called? For a of the momentum constraint, so of delta L xi, that is non-trivial. That is non-zero. This is what they proposed. Actually, I'm not exactly sure this is exactly the same, because there are terms that. This is 1 over 4a 7 Fij Pj. Then I tell what's Pj. It's not the mass, the momentum of the matter. R3S. This is the antisymmetric tensor xk. Okay. So what they propose, and they say, look, there's this trivial, there's this non-trivial solution. In this case, of course, you have 1 over r here, which is fine, which is parameterized by 6 numbers. Six numbers. Okay, So this is what they propose.
Equivalently, this means the momentum density is a delta function, pi delta, plus the gradient of a delta function, which is the spin.
Yeah, that's another way to put it, yes.
Because there are punctures have a delta function initially.
Yes. That's another, yeah. If you want to put the delta, yeah. And so this type of solution, these are actually called punctures. Or punctured black hole. And the question is, what are these parameters? This was suggested already. So one way to find out is, for example, you can calculate the ADM momentum, which is an integral similar to the one that we have considered before. And in conformal variable, it has this expression. And you find that this P ADM with an index down precisely corresponds to this P. And you can calculate J I as well, which is another integral. I don't put ADM because apparently this integral was never present in the ADM papers. But is now used. And in conformal variable, it has this expression where this phi are rotational Killing vector of each of these phi are rotational Killing vector of the flat metric. So something like x dy minus y dx with the right sign, and there are free component for each, and these are precisely then this S. So what you can do with this is that you can interpret this puncture, this is one puncture, but we'll see how to solve for more, as a spinning and boosted black hole.
Black hole. Particle.
Particle. Puncture.
It's not a pure black hole.
It's not a curved black hole. The question is that the point is that now you have this k, this x, which is different from 0. So your Hamiltonian constraint is not anymore the Laplace equation, but it has a term here, and it has also psi to the minus 7 that activate. So this term activated. So the Hamiltonian constraint is now a nonlinear equation for psi. And this needs to be solved numerically. So A tilde ij different from 0 implies that, how's it called, 3A, or the Hamiltonian constraint needs to be solved.
Implicitly assume there could be a sum over all the punctures with the distance.
Yes, and now I bring back this factor. So the interpretation here is, of course, for a single. If you pick one, this is.
Wait, if I put the spin to 0 and a single with momentum, is this a boosted Schwarzschild black hole, or it's not? Because the boost, as we discussed, the boosted Schwarzschild black hole is well defined.
I think you still need to solve the.
You don't, I mean, but we know the solution of a boosted Schwarzschild black hole, so.
This I don't know. This is another thing that I don't know.
Good
Yeah.
question. I mean,
Yes, good question.
But why is not a boosted Kerr?
This is not a boosted Kerr because it's conformally flat. This, if you take one puncture, 0p and s, this has a non-trivial evolution. It's not a static solution.
even without momentum, it's not curved.
Even without, yeah. So it's not Kerr. With p equals 0, it's not Kerr. For Schwarzschild, I need to think. I certainly have never done the calculation. So needs needs to be solved now numerically. So how to do it? Well, there's an ansatz which is informed by our type 3 calculation. So the conformal factor, it's an ansatz, so you can write what you want. It's the Brin-Lindquist factor, so here you can include as many as you want, plus a correction u, which, if you plug in now into equation 3, gives you an equation for u, which is an equation of this type. So this is again it's 3a again for the variable u, which needs to be solved numerically. It's nonlinear and looks tricky because one may ask, okay, what to do? Well, I have my asymptotically flat condition, which will have a certain value of u, say 0, and actually 1. But then what to do?
When we switched, you had 1, so now you need 0.
No. Here I define it with that's the piece. Yeah, yeah, but yeah, you can absorb it and then say 0. You can say okay, but what do I do at the points that I've removed? Well, there's a paper by Brandt and Brueggemann, 97, that calculates this at the puncture and show that at the puncture this term is actually 0. So this means you can solve this equation on R3 with the asymptotically flat condition only. That's what is done. So this is, I think that's the last comment. This is how initial data for these papers that I show of Baker and Campanelli, and since then everyone else, but even before those, people have worked with this data and calculated. This is how some binary black hole data, at least let's say most of the group are doing this, are calculated. So they take conformally flat data, they specify masses, boost spin if they want spin parameter if they want spin, and then they solve this equation on R3 with asymptotically flat conditions.
R3
minus, with condition that u is 0 at punctures. So
no, you don't need any condition on the of u at the punctures, because it's regular. It's regular. That's the key finding. So this piece is 0 at the puncture. Okay. So there are more ways of doing initial data. In particular, if you are interested in say very precise circular orbit, then there is an approximate Killing vector which you can impose in the construction of the initial data, and that helps you to get very precise data. But that typically is easy to apply in the other formulas that I have not explained. But some people are also using the other formulas. So, but this is just for completeness, but I'm not talking about it.
Can't we use PN or EOB
So what you can do, what is done sometimes, so here, if you want a perfectly circular orbit, let's say, you have to go trial and error, or have an approximate way to specifying especially these parameters. And then there are proposals by various groups that propose, for example, to infer the value of this parameter from post-Newtonian type of calculations. And this is how you obtain approximately circular data in this case. And then you can iterate between initial data construction and evolution code to experimentally minimize the residual eccentricity. This is how it is done.
Are these again Einstein-Rosen bridges near each puncture? Or they are more complicated? Before evolution?
No, they must be the same, right? They must be
Even with spin?
even with spin.
Could be complicated.
Could be complicated. Certainly, I never did it. I don't know.
Okay.
More questions? Okay, so the next, so now let's say now we have initial data. And so I wanted to spend some time saying how initial data are evolved.
Are you saying that in all, for instance, in the SXS simulations, what do they use? They don't use puncture data.
No, they use the other thing that I mentioned. So they use this conformal thin sandwich approach. And that is slightly different, but okay. So, but that allows to specify, for example, this approximate Killing vector, helical Killing vector, right? So circular binary is not static, of course, has no rotational symmetry, but if you follow the orbit, you should see always the same space. So this symmetry is called helical symmetry, and it's a combination of dt and d phi through the angular frequency of the binary. So within the actually within the XCTS formally, so it's an extended initial data formulation, but that uses this idea similar to here. It's easy to impose that Killing vector in the data,
But then
in the
it's
construction of the
formally
data.
flat,
Yes.
or-
Now we need to survive. Okay. Okay, after the initial data, we can talk about evolution schemes. And I will actually focus on what everyone does at the moment, at least in 3D. So free evolution. Free evolution is fine to do, and it means once you have a sigma 0, solve only what I call equation 1 and 2, or equivalent equation for those. And disregard completely the constraint. You can calculate them, but you don't use them. You don't solve them along the dynamics. This is at the continuum level. This is perfectly fine because we have proven it. The numerical level is a bit more tricky, but it's a valid approach, and it is nowadays used at least for all the 3D type of evolution that I know, and that say astrophysical simulation of black holes and neutron stars, they all use this type of approach. So how is the general logic? The general logic, as I said, solve only 1 and 2 given sigma 0 constraint solved. This is the short way. How? Well, typically the first step is to choose equation for lapse and shift. So one thing that I didn't say before, that if you look back at those equations, alpha and beta appears, but there's no equation for alpha and beta. But this is fine because this is gauge. But of course, you have them in the equation, so you have to make a choice. And we will discuss as a final topic, we will discuss how to make this choice in a clever way. But you have to choose equation for alpha and beta, or if you don't want to choose equation, you can prescribe them. So you can say, okay, alpha is 1 or beta is 0. That's the easiest thing that you can do. And then, okay, after you have chosen this, typically what you obtain, or you want to obtain, or look for, a system of equation where system I mean 1 and 2 plus eventual equation that appear for alpha and beta. So the entire thing that you need to solve, which you treat as an initial value boundary problem, so a Cauchy problem. And the system of the dynamics plus the gauge has to be well posed. Otherwise, it's hard to do numerics, because, for instance, you could find a solution that, well, it's not the unique solution, right? And so typically, what people do is to think and on the lines that I'm going to outline, and study hyperbolicity, properties of the complete system, and using those properties prove that the system that they are considering is actually well posed. So here I don't want to go into this, it would be too long, but what people look are property called strong hyperbolicity or a symmetric hyperbolicity. Yeah, so what this property do, these are essentially conditions on the eigenvalues of the principal part of the matrix that results from the principal part of the equations. Okay, so you know when you classify PDE, elliptic, parabolic, hyperbolic, you look for eigenvalues, and then depending on these eigenvalues, you classify the problem. In particular, for a hyperbolic problem, looking at these eigenvalues, you can in multiple dimensions, you can find cases in which you have real eigenvalues and a complete set of eigenvectors. This would correspond to strong hyperbolicity, and this is a property that allows you to prove that the thing is well posed. There's a stronger property, which is the symmetric hyperbolicity, which is the same, but in a sense that it doesn't depend on the particular direction, if you have three dimension, that you are considering. So this is a stronger property than this. Both of them allows you to prove some boundedness of solutions. So allows you to prove well-posedness. With this symmetric hyperbolicity, you can use some technique that are called energy estimate. I'm not an expert of that, but these are techniques that almost automatically, if you identify something called the symmetrizer that is related to this property, automatically tell you what technique to use to prove the boundedness of the solutions. This is for the initial value problem. In numerical relativity, typically, especially in this evolution that I talk about, we have a time-like boundary. We truncate the domain somewhere. So what we are really doing is the initial value boundary problem. So we need to have some boundary conditions in space. And this, in particular, this stronger hyperbolicity condition also allows you to develop boundary conditions. So it's something that is very useful. This you can do, for example, for the generalized harmonic, or for the harmonic gauge, which I'll then discuss. But this is the logic. Anyway, independent on the details, you have to choose, you have to make some gauge choice. And then with that gauge choice, look for the whole system and try to prove that this is well posed. And of course, these are nonlinear equations. So in many cases, especially for the boundary version, the best that you can do, actually no, every time the best that you can do is to prove something that is local in time. So you freeze the coefficient of the equation, you look at small perturbation on some background and prove all what you have to prove only locally. So a little step beyond the sigma zero. But this is the usual thing with nonlinear equations. So you always have to linearize them to then prove something. Okay, examples. Let's forget for a second about the 3+1 decompositions, and let's look at the case of harmonic coordinate or generalized. So sometimes it goes under the acronym GHG, Generalized Harmonic Gauge. I'll tell what it is.
Introduced by Helmut Friedrich.
Yes. An harmonic coordinate introduced by De Donder.
No, by
1912.
Einstein, 1912, used that.
1912, okay. You see the advantage of having. Okay, so we work in vacuum. And in vacuum, we have the 4 Ricci, which is, if you write with explicitly with partial derivative, it has this expression. So this is again the connection of the 4 metric. G is the 4 metric now. Plus here there is a term, I don't put indexes, but is of the form GG del G minus gamma gamma. Okay, so these are Einstein equation in vacuum written in terms of partial derivative, where gamma A is some contraction of the Christoffel symbol, like this. So this is a part that is you see nonlinear in the first derivative, but it contains at most the first derivative. So this is called a non-principal part. So it means it does not contain the highest derivative that are present in the equation. This is obviously the principal part. So for this hyperbolicity analysis, often you just look at this. And you see the structure. So the first piece is actually good. So the first piece is nothing. So when you put if you look at papers, when you only consider the principal part, they write in this way. So they put CMAC. This is box GAB. You see, this is a very nice D'Alembert operator with -1/2 in front. And the other piece instead is the problematic piece. But it belongs to the principal part. So you, in principle, I mean, you have to take this into account when you do an analysis. So this is plus A gamma B, and this is a problematic. In general, to perform analysis. So what's the natural choice to do it is to kill it. You take this gamma and you say, well, this gamma for me, it's equal 0. If you do this calculation, you find out that this is minus the coordinates. These are the wave, these are called harmonic coordinate or wave coordinate or what else? Isothermal coordinate, more. There are many names for this. But so at this point, you can say, okay, I have gauge freedom and I can make this equation look nice, such that from here I can start an analysis which is likely to succeed, and it will succeed because this is what has been proven long ago. So these are harmonic coordinates. Sorry?
These are the same that triggered Bois.
Yes. They were known before, but it's where you can prove a lot of things. Yeah. And there's a generalization of this. So you can generalize. And you can say, well, instead of gamma equals 0, I take gamma equal some function that I either prescribe or prescribe through hyperbolic equations that I can control. So these are called this generalized harmonic coordinate. And the advantage in some sense is that you can play. So you can play with the functions or with the equation that determine this function to have some properties, to have some wanted properties. For instance, you can play to have some nice, we will see what this means, but you can play to have some nice singularity avoiding properties. You can play them to drive your coordinate to have better coordinate for your simulation if you spot a problem in the simulations.
By the way, I got recently an email from Helmut Friedrich, who introduced it, telling me that for more than 10 years he talked to numerical relativists in AI and they never cared about this.
Ah, no, now this is really used. This is really used. Yeah.
But
This is a case where a mathematician said, I think this should be useful, and numerical relativists did not pay any attention.
I mean, you need to prove.
victorious.
Yeah. So I mean, you need to work and you need to, but
Yeah, it's not enough to say use that.
You need creativity also to make it working and so on. But nowadays, everyone that is using these generalized harmonic schemes play with constraint addition, play with this type of things in order to improve behaviors that they think is due to gauge, for example, that they don't like. And so this is actually. This system is where you can prove most of the things, and this is where what mathematicians like, what mathematicians have used to prove everything that could be proved so far. I wanted to mention something, that there's a way to see this. So if you now have this, you can write down an algebraic constraint, which you call Z, as the difference of these two functions. And so you can actually think of this generalized harmonic scheme as a Z4 scheme that I wrote before. Where now you impose this constraint at the beginning. So there's a connection between what we have seen before and what we have seen here.
Maybe with a minus sign.
So it is, I think this is a plus, but I don't know. So so there's a connection. So you can reinterpret what you have done so far by saying, okay, in Einstein, in GR, this is an algebraic constraint. It has to be 0, so I'm free to. And in fact, it's another way of having the system. And if here you remember the MHD thing, and you are free to add, for example, a term like that, or more terms. Actually, this is not the only term. This is a constraint damping term that dumps, say, in particular, this constraint. And so this type of game has been played, and this is one of the things that is listed in the Pretorius paper in this second column, that says he thinks is very important. So this is one of the things that he has used to actually make the simulation stable and running for what it needed. So
it was introduced by Carsten Gundrath.
Yeah, there's a paper of Carsten Gundrath that precisely write down in this form and shows the equivalence that I'm also discussing now. So this is taken from that paper.
Because Pretorius discussed with Carsten.
Yes. And so you can use, and this is nowadays is used in all the formulation in a way or another. So it's not only this, but this is the logic. So this you have constraint damping. When you read in the talk and someone mentioning type of constraint damping, it means this is what they are doing. Something in this direction. Okay. Now the other thing, so this is used. It was used by Pretorius. It is used by a couple of. Now SXS is using. In Jena they are using it now. Brugman Group is now using this. Actually, a lot of this calculation of the initial boundary problem for this particular scheme has been done recently by David Ildich, that has developed radiation absorbing and controlling, so constraint satisfying radiation controlling boundary conditions that are very important. There's a lot of work, and he could do it, of course, because of this property with this method. He's an expert. He has a review. I suggest to read that if you are interested. So this is used actually by many groups. So how about let's say the ADM, so-called ADM, the ADM equation. So if you now take the ADM equation that we have seen before, and you consider classes of choices for lapse and shift. For instance, you prescribe lapse and shift. For instance, you prescribe lapse from an harmonic condition and you set the shift equals 0, and so on and so forth. So the gauge condition that actually we'll explain later, most of those, the useful one of the one that I will explain later. What you find is that this particular formulation it cannot be proven to be strongly hyperbolic. That doesn't mean that it is not. It means, in fact, with other gauges, so if you take harmonic gauges, for instance, or harmonic type of gauges, and you couple, it is. So, or other choices. But let's say for the choices that work with the punctures, have not been found strongly hyperbolic. On the contrary, we found weakly hyperbolic, which means you cannot prove well-posedness. So people have looked at this. So why people have not just said, okay, then we forget it and look at the harmonic only? Well, because in principle, this allows you more freedom in the gauge. So here you can play with this H only, but here you can actually add any equation that you want. So you may want to explore a bit more this case, to have more flexibility in the gauge. And if now one look and does one look at the ADM equation as we have written down before, and as a partial differential equation, what you find in principal part is an equation like that. where this you need to symmetrize in A and K, A and I and J, and J, but just assume that I've done it. Okay, so this is the principal part in terms of PDE. Sorry, I forgot a piece. I copied the wrong line. This is correct. No, this is correct, but minus. So this is box IJ. Okay. And again, think about this symmetrized. But at this point, for this argument, is not needed. So you can set it to 0. So this is how the ADM equation looks like if you write them with beta equals 0 and if you look at the principal part and so on. And what you see is that you have a situation that is, in spirit, very similar to what you have for harmonic coordinate. So these guys here do form D'Alembert type of operator, not for G, but for the gamma now. But this guy here, which contains second derivative, so you do need to include it, is the problematic guy, basically. Okay. Now, of course, here you can say, okay, I kill this again, but then you fall back in sort of the other case. So the point is, how do we modify this type of equation in order to maintain the gauge freedom on one end, but remove, in some sense, this term from the principal part? The proposal goes back to Nakamura, O Ara Kojima, 96. So the idea goes back to these people. They say, okay, we can do two things. First, to introduce a new variable. And as a variable, we pick this guy. So we call it Fi, a new variable, which is the divergence of the trimetric. Okay? And then, instead of setting this to 0, which would be something, we say, okay, we use the momentum constraint to specify an equation for F, which is good enough. And how does this work? Well, you take F dot equal I, you want something like that, right? This is partial derivative with respect to time, partial derivative with respect to space of Kij. Now you can commute these two. So this is, let's call it gamma Ki dot. But now gamma Ki dot, it is something that, I make a long story short, you should do the calculation, but gamma Ki dot is something that is related to K. So it's the time derivative of gamma, so it must be K, right? Kij. So what you have here, you have the divergence of K. So you can use the momentum constraint, which is the divergence of K, to come up with an equation. So what I'm saying here, that here you can use something that will give you pieces of the momentum constraint. This turned out to be a good strategy, so in the sense that you can find good equation for F in such a way this system is strongly hyperbolic. And this is the route that has been followed by different, let's say, two groups. BSSN, so this stands for Baumgarten-Shapiro, Shibata-Nakamura, the same Nakamura, which use the streak not on the gamma, but on the conformally decomposed ADM. this will be important. Huh? So how it works, exactly the same. You find new variable, they call it actually Baumgarten. Shibata Nakamura use an F as a notation. Baumgarten use a gamma tilde, which is what is now everybody is agreed to use. Start from this, and using the same logic, gets an equation for gamma tilde, which is added, and that leads to a strong hyperbolic system, which is the famous BSSN type of system.
Has it been proven to be strong?
Yes, there are results from Gundlach and Martin Garcia. There are other results from Oliver Sarbach and other collaborations. This has been proven. It's also on the book of Alcubierre, the proof. And so this turns out to work, actually. And one interesting observation is that in this paper of Gundlach, of the constraint damping, they show that this variable plays the same role of the Zi variable. So again, you can interpret this somehow ad hoc construction as extending the system in a particular way, and as a Z3 system in this case, because you have only the special part here. And you remember, Zi dot was equal something like momentum constraint. So you see, it's the same thing. So this basically what this happens. So what you find then in the books, it says that this particular construction outlined here gives you better, kills the constraint violating modes. This is what you read in the books. And the mechanism is always the same. So is that by doing this, you have, you are propagating at least some part of the constraint. And of course, if you have done Z3, you can do Z4 and the conformal decomposition. So in fact, you can extend BSSN further in a Z4-like fashion, and you get Z4C, which is the Z4 conformal, which has even better propagation of the constraint, perhaps best, someone would say.
Who introduced Z4C?
There's a paper by someone called Friedrich and Bernuzzi, so two guys that met in our office. Okay, for the last part, now I want to discuss what I think is one of the very creative parts of numerical relativists or people working in numerical relativity. So it's the choice of gauge condition. Here you have no theory to do it. You have to be smart. So how do you want gauge condition? Well, if you've ever done something numerically, you know that in general what you want to solve on a computer is a formulation of an equation whose solution varies as little as possible, right? Because your solution is typically represented by polynomial. So if you have a constant, it's represented exactly on the computer, and you are exact, right? So if you manage to have a clever gauge condition that puts everything in a constant, well, of course, this is a trivial case. But imagine in any case that there is a gradient, and if this gradient is, varying a lot, this will give you numerical difficulties. If you have a solution that behaves like polynomial sufficiently low order, you may have a chance to capture it numerically very, very accurately, because that's the type of thing that the computer does. So you want gauge such that you have a smooth solution and that vary as little as possible. And you want gauge that, let's say, minimal variation, whatever this means. Or minimal gradients. Then, of course, you want a gauge, as we discussed here, that maintain whatever you have been able to prove for your equation. So if you put a gauge that violates well-posed, your system is ill-posed. It doesn't matter if you have proven something for that sector, or if the gauge sector is not well-posed, the entire thing is not well-posed. So this you want to keep. And another thing that you want to keep is that you want to deal with black holes, so with singularities that can form movement, gravitational collapse, black holes, and so on and so forth. This is very complicated in principle. So these are the general rules, but beyond this rule, you have nothing. So you have to invent something. So what's the easiest thing that you can do is what was already suggested, something called geodesic gauge. Geodesic gauge is the simplest choice. So I take alpha equal 1 and 0 shift.
These are called usually Gaussian coordinates.
They are also called Gaussian coordinate. Again, many names for this. In this case, so the Eulerian observer are free-falling observer. So remember that the Eulerian observer are what you integrate with your code. You are on that. In this case, you are free-falling. For example, your proper time, alpha is equal to 1, so it's your coordinate time. So the other way around. The coordinate time is your proper time. These are simple. They're actually good because by themselves they don't create extra trouble, right? If you have proven something well-posedness, these are constant. But of course, you cannot use them because if you again plot the Kruskal diagram, so this is 2m, this is 0, and you pick the slice that we have calculated before and start from this, an evolution with geodesic coordinate, you do something like that, and in a finite time you finish on the singularity. This time t over m, which is tau over m, is a pi. So everything that starts here in pi arrives here. So even if you have the best possible code, your code will simply fail for physical reasons. So you can't use it, but there's something that one can notice. At this, you can still learn things from this. So if you look at the acceleration of the Eulerian observer, we wrote it before. I think I forgot to put the formula that I needed now, but I can put it now. In terms of this, you can express this acceleration in terms of the lapse. And it is the simple formula. And if you have geodesic coordinate, of course, you don't have acceleration because you are free falling. So what this suggests, from equation 1, our kinematic equation, you can write an equation, you can trace it, and you can write this equation, but now this is 1 again. Okay, so this you see what I meant there. In a gravitational collapse, or in this case, say in a gravitational collapse, K gets large, and this means that the volume element gets smaller and smaller. What it means is happening is that in this geodesic gauge, you are in this, say, under gravitational collapse, you are under this conditions, and your observer are focusing, and at some point there is a singularity. Okay. This is the logic. I mean, this is the physics. But this equation now suggests you something, right? If I want to avoid to finish in a singularity, I have to activate the acceleration here through, for instance, an equation with the lapse, such that the acceleration of this Eulerian observer counteract gravity. This is the idea. So how would you proceed? First you find a cool name. This is called maximal slicing. And the idea here, which is actually contains most of the, I would say 50% of the secrets of the game, of the magic. The idea is precisely the same. So to find a way to impose an acceleration such that you avoid this focusing. And how to do it? Well, for instance, you can consider the expansion of this observer and set it to 0. So you have a condition like that. But a condition like that is nothing else than the trace of k equals 0. That's why at the beginning I said, at some point I said, k, the trace, is a natural gauge condition. Imposing, choosing as a free data is a natural gauge condition because of this. So this is an incompressibility type of condition. So if n instead of our observer is a fluid, this is an incompressible fluid. So in the language of fluid, this would be an incompressibility condition. In our language here, what instead of incompressibility, we would use singularity avoiding. Singularity avoiding gauge. Okay. Then the cool name, maximal slicing, it's because of a parallel result, but it's related to this. It's in between, actually, the lectures, right? So you remember when we say the minimal surface, the divergence of S is 0. This is the same condition, but with a different, well, with the minus sign because it's a signature. So there is, this condition is actually maximizing the volume of the slice. That's why it's called maximal slicing. In general, if you do something like that, you are extremizing something. So, but anyway, this is just to tell you the origin of the name. But what we care at the moment is that this looks as a promising, for this argument, this looks as a promising gauge condition. So, examples. Do we know some of this maximal slicing? Okay. Do we know some of this maximal slicing? Yes. So if you take again a Kruskal diagram, 2m r equals 0, and so on, in standard coordinate. So if you have slices of standard Schwarzschild time, let's call it like this, these are maximal in this region like that. And in principle, you can continue them also in the region 3. Some funny thing happened, now I will discuss it. But what happens when you go in time, these slices are doing this, right? And they are singularity avoiding in the sense that they never enter region 2. So they do have the property that we wanted. Right? They also have bad properties because these slices, they are all crossing here at the throat. And on the region 3, they even go backwards. Okay, so strictly speaking, some people would not call this a foliation. This is not foliation because the slices are all crossing. So this is something that we may want to improve, and it's possible. But already in this simple example, you do see that the idea works. The slices, they never enter region 2. So it's this one, region 2. This is 1, this is 2. So, yeah, this is, so here lapse is 0, which is a problem, and they run backwards there. So there is a better foliation of Schwarzschild. The way to do it is to consider a transformation of this type. So this is Schwarzschild time, and you send it Schwarzschild time plus a function of Schwarzschild radius, and solve, and you can solve k equals 0 for h. So what you are doing here is introducing some shift. And you can do this, and there is, you can find a family of solutions. And pieces of the members of this family are actually symmetric through the point here, and in general symmetric with respect to the axis. They are of this type. They look like this. Now I'm sketching them, and they have an interesting property. First of all, they enter region 2. Here they do enter, which might be fine, right? Because we do want to, but they have a limiting for proper time large. They actually have a limiting slice which stays outside the singularity. So this is 3 m, should be blue. So that you can calculate this. This is a limiting surface. Let's say for proper time large. And you never enter beyond that. You never go beyond that. Okay? So again, if you do this, this is singularity avoiding. So this has been experimented a lot with computer codes and so on, and this is what has been found. There's a result by Baig and Muharda, 98, that they also show that the lapse goes to 0 in this limit, goes to 0 exponentially. And this is again another property that is common to all the gauges that are singularity avoiding. What it means is that here at times is slowing down, and this slowdown is precisely one effect of avoiding this phenomenon of focusing. So it slows down, and you never enter inside. But in order not to enter, you need to freeze. So this is called. This is what people call lapse collapse, or freezing, lapse freezing. And it's not only a property of this particular gauge, but then it is observed also in other singularity avoiding gauges. Perhaps a comment here. If you look at the embedding diagram of this, the embedding diagram are like that. And here you have asymptotically a cylinder with radius 3 m, which is not an asymptotically end. There's this thing here. And so for this reason, because this is very long like this, it's called trumpet. They are called trumpet solutions. This is not asymptotically flat. So a generic fact, and then I switch to something else. A generic fact is that if you impose this equation, you can do the calculation through the 3+1 decomposition, and this typically results in an elliptic equation for the lapse. So to summarize, maximum slicing is a singularity avoiding slicing, avoids the singularities, for example, in this particular case. Typically, when this happens, you have this phenomenon of lapsing, collapsing, or freezing. And in general, if you want to impose it, you need to solve elliptic equation for the lapse. This is the type of equation that they are coming out. So the last thing that I want to say in the gauge thing is here. Is that within a free evolution scheme, if you couple your hyperbolic equation with an elliptic equation, you get a more complicated system to analyze. So sometimes it is you desire to have just hyperbolic equation, okay? But there are, so hyperbolic gauge, better, let's call hyperbolic slicing condition. So there are hyperbolic slicing conditions that mimic exactly this, but they are in hyperbolic equation. And a popular one that now everyone is using as this type is of this type. I think there's a k-square here, but I don't remember actually. Someone remember? No. Okay. So where F, this is called Bona-Masso type of gauge. And so for F is a generic function, so you can take it 0. This would include also the geodesic gauge. In this case, it's not interesting. You can take it. Is equal to 1. This is harmonic gauge, or better, harmonic slicing, because it's only. It's only time.
And this is the Schocker-Ruggieri.
Yeah, so it is really this type of thing. Or with punctures, what has been found is something that is called 1 plus log. Let me not comment about this name. There's a reason, but it's a bit involved. So if you make this choice, this is called 1 plus log gauge, and it has been found to reproduce with this hyperbolic equation a behavior which is very, very, very similar to this. And so this is what it is used with these puncture evolutions. And I still have one topic. No, not topic. This is the last. Yeah, after then there are the slides. But, okay. Then I can go fast on the slide. We get back the 10 minutes from. Okay. So what we haven't discussed so far is the spatial gauge. So far we just discussed the slicing. So conditions for alpha. Spatial gauge. Okay. So what beta to use? So again, beta equals 0 is in principle a good choice because per se it does not introduce extra problem. But for example, what is observed if you have again gravitational collapse and so on, and you use one of these singularity avoiding slices, you see that in some places the time freezes, so the evolution effectively stops, but in other places far from the singularity it continues. So you can imagine that spatially you may develop very large gradients, which is something that we didn't want. Another thing is rotation. You would like a gauge that is somehow adapted to, say, Killing vector, if you have a stationary rotating thing, and without shift is hard, or you cannot have it. Okay. So one idea that goes back to Smart and York, 78. Is to say, well, we found now equation for beta by minimizing something that they call the distortion tensor. Which is a quantity, say co ij, which is gamma dot. So they basically want to minimize gamma dot ij. But they remove the trace for a reason that now I tell. And this turns out in conformal variable to be psi4, the derivative of the conformal variable. So what this tensor attempts to measure, okay, I don't know it anymore, but what this tensor attempts to measure is, let's say, the change of shape from one of a certain domain from one slice to another. This is what has been. This is the heuristic that is behind it, and the shape and so the shear, if you want, and not the volume, because they remove the trace. This is now the dt. This is the heuristic behind that. And well, you can write for instance, one elegant way to do it is to write a functional on some sigma t of q square, and then go and minimize this one and find an equation for beta. This is a way to do it. And what you find is that, of course, this minimization gives you the divergence of this guy has to be 0. This is just Gauss. And then this gives you an elliptic equation for beta, which is of this type. So this is the operator that we have seen before. And here there are terms, but I mean, you can even discard some terms because, in fact, you don't care about the precise equation. But essentially, this gives you an elliptic type of equation for beta. Okay? And again, for the same reason as with the lapse, what people want are not elliptic equation, but hyperbolic equation. So people have developed a set of gauges that they call gamma drivers, and they are constructed like that. First of all, you impose a simplified condition with respect to this one. So instead of saying that the divergence of Qij is equal to 0, a simple expression is to simply ask that 0 is the partial derivative of the time derivative of the conformal metric. So this is a simplified version of the equation that has been derived from there, but there, I mean, there's nothing fundamental to that. It's just an heuristic argument that brings to this. So if in the end this works, you are perfectly allowed to use it.
And this is the Dirac gauge.
Yes, it's connected to that. Yeah. And the advantage of using this is, again, you can flip things, and this can be written as the time derivative of this gamma tilde variable that are in the BSSN system. This is why this is used with the BSSN system, obviously. So gamma freezing, because it's the derivative of gamma equals 0. But of course, this is the same type of equation, so this is equivalent to having an elliptic equation, which is now simpler than the other, but it's still an elliptic equation for beta. But at this point, we are not very afraid because we know how to translate. I mean, we have freedom to translate this elliptic equation into, for instance, parabolic equation. And that is where driver, the word driver comes in. So you can say, okay, instead of having an elliptic equation that instantaneously decide my beta, well, I can say that my beta is the solution of an equation that goes like this, which means it's a sort of it equation. I can put the coefficients, that would be my diffusion coefficient. And so beta would behave, I don't know, like temperature. So asymptotically, one expects the solution of this equation is the solution of the elliptic equation here, right? Because you will have an exponent, you will have an exponential behavior like the temperature, for example. This is parabolic, because this is first derivative. But one can do also hyperbolic version. So the driver here, the word driver means that you introduce time derivative and parameters, and the time derivative drives the solution to asymptotically, in some sense, to a solution that is similar to this one. So the hyperbolic gamma driver will be again something like 2 derivative beta equals some speed of gamma tilde I, which is again something you can actually take as just elliptic of the operator applied to beta, because you can discard everything. You are free to do it. And if you really want, you can even put a damping term, since we have learned that this is useful. And so this is what is called the hyperbolic gamma driver. And this is what is used with puncture, together with the 1 plus log. Now, the key observation for successful puncture evolution, so what I show in this paper by Baker and Campanelli, you actually find it in a paper of Alcubierre, Broom, and other people 2 years before, where they do a calculation. They use this gauge, they use BSSN, and they calculate the equation at the punctures, and they state in the paper that a non-zero shift allows you to move the puncture on the grid. Then why they didn't manage to make it working is mystery to me, I will ask. But that's the reason. So it's not magic, right? If it comes from clever choices. I mean, the puncture method works because there are clever choices of gauges, and then the equation do the rest. Sorry, this was a bit fast, but I think you were all tired. I will quickly go to the slides. So this is actually a game that I play usually with the students at the first lectures of the long class of numerical relativity. And this tells you exactly the story of the gauge, right? So this is Schwarzschild. This is Schwarzschild, space and time. And the points are your grid points in your computer. And in this case, it's geodesic slicing. Alpha is equal to 1, beta is equal to 0. You start from this slice. You advance in time, and this is what we have just discussed, and you finish into the singularity. And that's why the code crashes, because the first point in your code crashes against the singularity. Something that is used and is still used, and this is what Pretorio used, is something called, not geodesic slide, but something called excision algorithm. So if you don't know better than do it this slicing, what you could think about, some clever algorithm that systematically remove points as they enter the horizon. And these are, of course, not associated with this gauge, but these are algorithms that are in place. So Pretorius used it, SSX used it, other people used it. But then the logic is this, that you would have a successful simulation because you remove points. Of course, if you use geodesic slicing, you still will not have a successful simulation because at some point you will remain with 0 points. And this is what, instead, this red, is what the singularity avoided slicing, for example, something like this, would do. It would start like this, and then here time would freeze as you go in, But here it continues to go. So it goes much further than the other red. But at some point, you see, you will have big distortion. This is still with shift equals 0. And now, sorry for this very crude visualization, but if you add a shift, the idea is that you make these slices to bend less and also to stay a bit away from these regions here. So this is effectively the qualitative thing that happens. So, actually, if you want to have a proper discussion of this is written in this paper. And as I said, this works. So this is I think the conformal factor in moving puncture. This is a simulation. This is not a cartoon. This is a real simulation of a gravitational collapse. Actually, this is spherical symmetry, I think, where you see a coordinate, so coordinate of the simulation, and you see the blue. It is the Schwarzschild radius. So you see that the coordinates actually are stretching, if you want, the grid in the direction that allows to continue the simulations. So here, this is the surface of the star, it goes in, and here an horizon forms. So effectively, there's a stretching with respect to the other coordinate, whatever you take. Here I have a nice visualization. So now this is just showcase of. I have two slides where I want to showcase a little bit a few topics. So numerical relativity is not only binary black hole problem. So nowadays we do very sophisticated simulation for astrophysics. So this is a binary neutron star. What you see is the mass, is the rest mass density. You see these are constraints satisfying initial data in circular orbit with this approximate Killing vector. You see there's a complicated flow, and then you see black hole formation, a disk. This is all consistent in general relativity. You look at the disk, you look at waveform, material that is ejected, that produces electromagnetic counterparts. So this is really advanced quickly in the last, I would say 15 years, but a huge boost also about these things in the last 5 years. It was really impressive. So this is with microphysics. This is with neutrino radiation inside. So the T mu nu is not just perfect fluid. This is something very complicated. You have to change. Okay. Okay, and here is the computer that we use in Munich. This is actually not the latest say version of newest computer. So nowadays we have exascale computing. So exascale computers are being built actually, and some of them are working in the world. But
That means what already?
flops, yeah. So this is so as I mentioned before, this IBM 70 or 90 is around hundreds of flops per second. So this is petaflops. So this is what we are working with, and that allowed these big simulations, of course. There were also kind of sort of surprises, quantitative surprises. So we know that there could be kick. So if a binary black hole merges, you can have a kick of the remnant because of conservation of linear momentum. But people quickly discovered that there are special configurations that give enormous kick. So this would be kicks of thousands of kilometers per second or so. So this is astrophysical. This is a GR prediction now from these things, and these kicks could kick the remnant outside the host environment, galaxy, whatever. And so it becomes very, very astrophysically relevant, and quantitatively it needs clear prediction. So this was also there's a series of work. These are 3 of my choice, but famous ones. But numerical relativity is not just focused on binary black hole. There's an important, I would say, a line of research that has started in '93 with these 2 papers. So in short, what has been found first by Choptwick in 1D with the scalar field is that if you consider some matter, and you may ask, okay, I put some matter with some energy content, what happens to this matter? So there is a regime where you don't have much energy, let's say, and then this matter disperses. But if you put a lot of energy, maybe in a region, what you may expect is that there's black hole formation. Okay, so he studied these things and discovered that actually the threshold between dispersion and collapse behaves similarly to critical phenomena in statistical mechanics. And so with everything associated, so that black hole formation has a parametric dependence from the initial data parameter of this type around the threshold. There's a self-similarity in space-time, so it means that if you are at the threshold and zoom in space and time, you find that space and time is actually self-similar. And they actually calculated exponents and argue about universality and so on. And you can, and soon after, you don't need to have matter. This happens also with just space-time. So collapse of gravitational waves, in this case in 2D, this paper showed that there are all these phenomena. So something that is maybe fundamental. And there's a lot of work, especially now with sophisticated code about this. There are also other things that have been studied. I'm not an expert of that, but people have looked at high-dimensional type of black holes, instability. So there are some solutions like this one. So this is a solution that is called 5D black ring in an asymptotically flat spacetime. So a solution that has I think this is curvature that is of this type, and you can calculate it analytically, but then you don't know if it's stable or not. And you can evolve it, and you see that it is actually not stable. So it develops in this sort of shapes, and here actually, I think here is curvature that goes. What was this? Yeah. So here you have formation of potential formation of naked singularity. So now I don't want to comment in details too late, but. There are this fundamental aspect, also more exotic, that can all be now explored with numerical relativity. So, sorry I'm late. This is my conclusion. So, there's been a huge progress in the last 60 years. Holy Grail has been reached in some sense. So, there are successful simulation of binary black hole merger. And now we provide, with this simulation, precise calculation of what the gravitational wave is supposed to be. This is mostly due to a relatively good, not complete, but relatively good understanding of Cauchy problem, initial data problem, which we have a bit discussed. Creative solution for coordinate choices, so what is here in this blackboard. What I didn't discuss are dedicated numerical method that we are using, and also technology, right? Because without such a big computer, nowadays we will not be able to do certain things. So nowadays we can handle all these astrophysically relevant cases fairly well. There are a couple of different approaches to actually calculate things, so also this is also good. And we have sophisticated method. I'll show you a movie, nice colored movie, and people are also studying fundamental aspect of gravity of other type, and there's much to do. So this is the message. So the method to generate initial data are definitely very few. Particularly non-conformally flat data, generic data for matter, boundary condition. There's a lot of, in principle, there should be a lot of work on these things because they're very critical. There are people working on robust method to incorporate null infinity in the simulations, in particular paraboloidal methods. Cosmology, people are trying to apply some of this technique in cosmology, which is a different type of, which is not what these methods are born for, but and there's also a lot of work that is very little and almost never discussed about developing more efficient and precise numerical method for the evolution. And finally, some of many groups, I would say, they are now start thinking about the new hardware, and new computers are actually coming. They are different from what they have been in the last 20 years. And so we need to learn also to use now this new technology, which will be fundamental to really move on. Okay, sorry if I was late. Thank you.